Hi everyone. I thought I'd make this short video to let you know how my SNR estimation app is doing. A few weeks ago, I created a signal-to-noise ratio estimator app based on math shared on Cloudy Nights by Craig Stark. If you haven't seen that video, check it out first. I thought I'd update the community to some of the hiccups that the app had, how I fixed it, and how the estimates compare to real-world data. Also, if you've been watching these videos and enjoyed them, consider subscribing. Welcome to Deep Sky Detail. Okay, what are the hiccups? Well, a major step for getting accurate results is converting how many photons need to hit your sensor in order for your camera to register it as an electron. The camera gain in electrons per ADU is instrumental to this. There is a bug in the code that inverts that number, which is fine if you're using unity gain. Unity gain just means one photon equals one electron sent as a signal to the camera. But the bug is not fine if you are not using unity gain. Anyway, thanks to the users who caught this. It was an easy fix and now the app should work correctly. So how accurate is it? Does it correctly predict how many stacked images I'll need to get a desired signal-to-noise ratio? How can we even measure signal-to-noise ratio in real life anyway? Well, we need to know the signal of the stacked images, and we need to know the noise of the stacked images. Then we take the signal and divide it by the noise. Should be pretty easy, right? Well, kind of. What are we measuring the SNR of? Individual pixels? We could do that. The problem is, individual pixels by themselves aren't that interesting. When you view an image, your brain generally averages over a set of pixels. So do we then take an average of all the pixels in the image? Well, I think that's too broad. I think the best approach is to take a sample of pixels from a limited area of the image, and the signal-to-noise ratio that we calculate will be for that area. For my test, I'll use the core of Messier 101 that I took a couple months ago and take a sample of 30 pixels. Now we have to figure out how to measure the signal of those sampled pixels, as well as the noise. So let's think about this for a second. Signal is just how many electrons are hitting the sensor from the deep sky object that we are imaging. So basically, it's the brightness of the pixels we are interested in minus the sky globe background. That's pretty easy to calculate for one image. However, what if we want to stack 10 images? How do we calculate the signal then? Well, when we open up subframes, the shutter is open. Let's say that for a target pixel, 10 photons from the galaxy hit the sensor each minute on average. But the target value will have different values on each subframe. Sometimes 10 photons will hit the pixel, sometimes 8 or 12 or 15 will. There's a randomness to it. When we stack images, we're just averaging each subframe. That means the signal for one sub will be the brightness value of that sub. The signal for two stacked subs is the brightness value of sub 1 plus sub 2 divided by 2. The signal for 3 stacked subs is the brightness of sub 1 plus sub 2 plus sub 3, all divided by 3. This pattern keeps going. In other words, all we have to do is stack a sub, find the average brightness, stack another sub, and keep going. That's not too bad. Additionally, we need to subtract the average sky glow of the pixels too, by selecting a sample of pixels from the background. So what about the noise? Well, noise is not complicated either. Noise is just how much the signal changes on average as we stack the images. If a target pixel in one subframe is really different than subframe 2, that would be bad. We'd have a noisy image as the signal of the two stacked subs would be much different than one subframe by itself. So standard deviation is a good statistic for this, but it's a little bit complicated as to how we're going to implement it. First, we're going to implement the noise measurement in a similar way as the signal measurement. except we can't just take the cumulative standard deviation of the signal. We'll find the standard deviation of the 30 sample pixels for each subframe. We'll then stack a subframe and find the standard deviation again. This new standard deviation value is not our noise measurement though. What we need to do is find the standard deviation of the two standard deviation values. I know it's complicated, but doing it this way helps make sure that the noise estimate doesn't depend on the number of sampled pixels we have. If we average 30 pixels together to get the signal measurement, we're essentially stacking them. This would artificially decrease the noise measurement. So if I just took the cumulative standard deviation of the signal, it wouldn't work. Taking the standard deviation of the standard deviations gets rid of that problem. As we stack more and more subs, the true standard deviation of the 30 target pixels will emerge. That number will get more and more precise. Taking the cumulative standard deviation of the standard deviations will then show us how the noise is decreasing. So there is still one problem. How do we make sure that a target pixel is measuring signal from the same part of the sky each subframe? Well, luckily Serial can help. When stacking, Serial will register each subframe. Each subframe is then aligned with a reference point and saved as a registered image. All the registered images are aligned. Here's an animation of 1700 15-second light frames to show you what I mean. Everything stays lined up more or less. Also note that there's a lot of variation in the sky globe background of M101. This will be important later. But generally I started imaging M101 each night when it was low in the sky until it reached its highest point. So we have 1700 15-second light frames from M101. We'll find the brightness values of 30 registered pixels from M101's core. Then we'll measure the noise of those pixels to find the signal-to-noise ratio. Let's also do a visual recap with just one target pixel to make things simpler. Here is the brightness of one pixel over those 1700 subframes. As we stack, we'll keep averaging the brightness values to get the signal. Here is the cumulative average as we stack for that pixel. As you can see, the average brightness of the pixels fluctuates less and less the more images we stack. The amount of fluctuation is the noise we're computing, the standard deviation, represented by this line. When we divide the signal by the noise, we get the signal-to-noise ratio. Okay, so let's do the same thing for all 30 pixels at once. And here's the result. So how does it compare with my SNR app? Well, let me just open up the first raw file I see, get the sky background and target values and put it in the app. Oh no, it doesn't match up at all. My app must be horrible. Wait a second. Let's go back and look at that light frame I chose. It was from April 12th at 1:36 a.m. At that time, M101 was almost at its highest point in the sky. Transit was only 20 minutes away. Now, I don't know about you, but I don't want my telescope outside all night. And I have a full-time job, so I usually don't image all night. Around midnight or 1 a.m., I'll usually stop imaging and take my telescope back inside. So for M101, I generally started imaging around 9 p.m. and finished at 12 or 1 a.m. The subframe I chose was probably the best subframe in my whole stack. It was high in the sky and was least affected by sky glow and light pollution. It's not a good representation of most of the other images. Let's take a random image from about 11 p.m. or so. And when I say random, I literally just picked one that was in the middle of the list. Okay, let's put these new values in for the SNR app. Holy moly! At 1,699 subs, the app predicts an SNR of 95.3, and the actual data shows an SNR of 95.7. Okay, let's try that again. At 504 subs, the app predicts an SNR of 51.9, and the data say 52.6. That's honestly not that bad. When I first created the app, I thought it could only be used as a rough estimate, but seeing these data now makes me think that as long as you use an average subframe, you'll get really good results. Let me show you one final graph. This first line is the SNR that we calculated based on the real-world data. The next line is the SNR based on one of my best subframes, and the final line is the SNR predicted by an average subframe. So it is the takeaway. When you use the SNR app, make sure you're putting in values for an average subframe. Don't use your best frame, and don't use your worst. The app is probably best when you're shooting the same target over multiple nights. What you'll want to do is image the first night, find an average subframe in terms of sky globe, background, transparency, and whatnot, and use that with the SNR app. As long as the other nights that you image have similar weather and moon phase, you'll get pretty accurate results. If you use a subframe that isn't average, or the nights you image have wildly different transparency or moon glow, all bets are off. I ended up getting about 27 15-second subs of M101, or about 11 hours of data from my light polluted neighborhood. I figure that the average SNR of the core region is about 120. Here's the final results. And thanks for watching.